It is working. Hi guys, hope you guys are doing all right. This is the video for problem set 2 for econometrics. Just fair warning, right out of the gate, I didn't quite get the last bit of question 1 for this. It's still a bit of a mystery to me. I've given my best guess as to what the answer is, but I am aware I'm missing out a few bits, but fair warning. We've got the 4 bits here. We've got the problem set document. We've got my solutions. We've got a bit of Stata for the second question. And we've got the description of the variables. So, actually, first of all, I'd like to start on on the Moodle page, there's lecture notes. I find these very, very useful. If you go to, I'll show you guys where it is. If you go to resources, textbook, Stata guide, datasets, lecture notes, it's in the same place you found them. The lecture notes are here. It's in the same place where the Stata datasets are. Look at these because they're very useful. Also, having the slides open like this would be very good. Let me delete those as well. But yeah, and I think this is just the PDF of my problem set. Okay, well, first of all, we don't really need Stata right now, so let's get rid of that. Okay, let's consider the following. So we have a regression model without an intercept, okay? And it's based on a random sample from the population, which we're assuming is just a random combination of y and x, any of them basically. And we wish to estimate what beta 1 is, okay? Now, fair warning, I think this question uses beta 1 with like a tilde on top instead of a hat. I'm pretty sure that is estimated B1. It's sort of like B1 with the hat. I think they're just using a different sort of look here. So just so you guys know, I think that's the deal. So just know that. Okay. So it asks us to write up the sum of square residuals for the model and derive a first order condition of the OLS estimator, which we denote as beta 1 tilde in this case, which actually reminds me I should probably change that. I'll do that after. Don't write it with beta hat. It's beta tilde. Of beta has to satisfy the first order conditions. Show that the solution to the first order condition, that is the OLS estimator, takes the form, and then this. Right. This is probably where you guys are getting it's like, oh my god, how do I even start? So first of all, it's good to know a representation of the sum of squared residuals. So the sum of squared residuals takes this form here. So it's going to be the sum of basically u squared, because that's the residual. So it's the sum of all residuals squared. Pretty simple. So it looks a bit like that. What we do is I think you can see this in one of the slides, if it comes up. Where is it? So it's like, I think it was in one of the more recent ones. The problem is they don't date these. They're just random numbers, so it's a bit weird. Was it here? No. It was somewhere. Hold on, I'll just flick through. Here it is. Yeah. So you can see it in these slides in the famous slide number 18 FAD 4F3 F18 DC. They're not labeled very well, but it's in this one. It's the one with multiple linear regression analysis, interpretation, and estimation, and it's down here. So you can see that SSR is represented as this. This is with multiple variables, and then you partially derive in order to get the first order conditions. Okay. Here we just have one variable, so we only need to get one first order condition. You can also see here that we can suggest our moment conditions here, which I believe is also in this one, or it's not. Basically, the main thing with this question is that you're looking at the slides, pretty much. Also, I have to do this quickly because I'm going out for dinner in 40 minutes, which is fun. Where is it? Jeez. Is it in here? Where's the moment conditions? Was it in a previous one? You guys are going to have to be patient with me. Probably skip ahead at this rate. That's not it? No? Where are they? We're just missing it. Where the Can you see me still? Hold on. I'm just checking. Do I dip below frame? I do a little. Okay, let's not do that. Oh, they were here. Fuck. Here's the moment conditions in the population. Okay, so yeah, you have these two restrictions. So you have basically the estimated value of u is 0, and the estimated value of u times x is also 0. Okay, so using those, okay, we basically insert what our value of u is, which is y minus beta 1x, as per our thing over here, because you can see u is equal to y minus beta 1x. So we're inserting that stuff into our moment conditions, and then we use our sample analogs of our expressions, basically. So this is the next bit. So you use these analogs for our conditions, and then eventually you can rearrange the sample analog, because we just have one, because we have one variable. So rearranging this, you get what looks like this, and then if you divide this for the estimation of beta 1, you get this expression, which is sum of xi yi over sum of x squared, which is equal to the estimated value of beta 1. So that's number one. I know, a bit complicated already, but do try to be patient with me. I wonder if I can... Give me a second here. It might be better to put fancy zones on and do this. I hope this is still recording. Do this grid. All right. Yep. Okay. So this one can go in the middle. This one can go to the sides. And where's this? This one can go to the sides. Okay, I think that should be easier. Okay, now for B. It's quite easy, honestly. Under which condition is it well defined? Well, basically, definition means that the denominator can't be 0, and that's the case when x squared isn't 0. So when x squared isn't 0, it's computable. That's pretty much it. At least that's what I got. Okay. Again, remember to do your own work and don't don't rely on me too much, because I get shit wrong sometimes. In fact, quite a few times. But yeah, regardless. So for C, we have suppose that the estimated value of u given x equals 0. So that's the zero conditional mean assumption. SLR 4, yes. Show that the estimated value of beta 1 is an unbiased estimator of beta 1. Now there is, in the lecture notes, this section, unbiasedness. And this actually gives you basically the step-by-step thing. Look, it says, here we show that the estimated value, basically it's a proof of unbiasedness. Going through this isn't perfect, because it's technically it's for something with a constant, and we don't have a constant. So the stuff is, it's kind of weird to go through it, because it's using difference instead. But I'm going to go through it. It's basically the same process. So starting with this, we can essentially break down our summation from previous one in 2 steps. So we separate out the top, okay, and then we split it out as well. So we're factorizing it, then we split it, and then because it splits into something with x squared and x squared, we can cancel it down, and we're left with beta 1 plus what we consider a sampling error, essentially. And to prove it, we have to show that the expected value of this resolves. So basically replacing that with this, what we got earlier, we can show that we can essentially cancel out the sampling error. And we do this by essentially bringing stuff out. So we take out the bottom, first of all, because it's technically just a constant. We're looking for the residual here. And we're continuously taking stuff out that's constant until we're left with expected value of u, which we've already established is equal to 0, because it says it somewhere. Yeah, it was established in our zero conditional mean assumption, essentially. It was also established somewhere else. Here, the moment conditions. Basically, the expected value of the residuals should be 0. And that's why it equals 0, equals 0, equals 0, and you're left with just beta 1. So that's showing it's an unbiased estimator. If you want something in more detail, you can look at the lecture notes. They're basically just here. This will probably break it down a bit better, but the problem is they use SST, not SSR. So it's a bit of a different thing. So don't take directly from here, because it's not the same. a beast, really. So for D, and this is where it sort of gets a bit sketchy with me, suppose that the variance of u given x is, standard deviation squared, or sigma squared rather. Derive an expression for the variance where the xn, or fancy xn, is basically every x value. Okay, it's the set of x values. So for the set of x values, give the variance of this estimator, essentially. So we're using that, and what we get, okay, well, at least what I got. So we've established at the start that the variance is constant. So this is the homoscedasticity assumption, or SLR5. Homoscedasticity is the homoscedasticity assumption, and it basically asks to derive an expression. So we can replace the estimator with our actual value plus sampling error, and what we're going to do is we're also, and this is also in part 5 as well. These lecture notes are really helpful. So fucking, why is there always an ambulance outside my window? It's insane. But yeah, basically what this says and what this gives us is that you can use, basically it's the same thing. You can replace the xn with xi, basically for any x value, because they essentially are the same thing. So those two are constant. And what we're going to do is we're going to separate out this term we had here, the xui over x squared I, into x squared, just to make calculations for us easier. They do this here as well, so I sort of followed suit. And we're going to label that wi to make it a little easier for us. Feel free to pause and look at this in more detail if you're having some trouble. We can now give it a new expression for the variance, because beta 1 is left out, because beta 1 is a constant, so it wouldn't affect variance. Basically, any constant that's in your variance doesn't affect it, so you can take them out. So we take out the beta 1, and we can simplify it even further. So we take out the summation, we take out w squared because it is still constant, and we're left with u, variance of u given xn. And because we said that variance of u given xn was sigma squared as well, we replace it. So we end up with this. See here, so sigma squared, and also because it's a constant, we move it out. So we end up with this. And then what happens is that we bring back the wi to what we had before, and we further simplify from there. So you see, we've got the expression previously, we've squared it. Because it's the same expression twice, so it's x over x squared, it's essentially 1 over x. And then we square it again, because, well, that's what we do. That's what's dictated by our calculations. And we end up with, well, bringing in the sigma again, we have sigma squared over summation of x squared I. But because, well, if you think about it, so this is the summation of all x variables squared, essentially. So if you think about it, taking every variable, squaring it, that's the summation of it. That would be the equivalent of taking the average and timesing it by the number of stuff. Basically, that's the sum, okay? And I think I've made an error here, because it should be overline x squared and not overline x. At least I think it is, yeah. So let me change this around. Whoops. I think that's that. Yeah. So basically we're just making it a little simpler for ourselves, but that's that. Okay. This, for me, I did feel a bit sketchy about doing this, but I feel like I've got a generally the right idea. E and F here, I wasn't really sure about at all. So please take it with a grain of salt. I've just got what I think is right. So it says provide an estimator of the variance that you derived in D. Now, I remember from first year that when we were told about, basically an estimator of variance, standard error works as an estimator of variance. So I'm using standard error of basically the estimator for beta 1, and that would be the sigma value over root n, essentially, because that's the formula for standard error. That is at least what I'm going with. That's that. F, I'm even less sure about. Okay, so suppose instead that the data is in fact generated by the following regression model, not the Stata one, but now it has a constant, essentially. Will beta 1 in equation O2 be a biased estimator of beta 1? If so, derive the bias of the estimator. Okay, so here's the thing. Deriving the bias of the estimator, I think I figured out what the bias is. I think it's positive, okay? But I did not derive it. I don't know if derived it can just mean find, but I'm going to go with it. You're just going to have to go with me here. But yeah, so I'm saying it is a biased estimator because there is a slide. Hold on. You just give me one damn second. Where is it? Bias? Here it is. Can you guys see that? Yeah, it is unbiased in two cases. This is the case where it's unbiased, where the other variable is 0. Okay, so because we now actually do have a constant, it cannot be 0. Okay, because we brought this constant. Imagine the constant was there and it was just 0 before. Now that we brought it in, it's not going to be 0. So this already is false. So it has to be biased. And then covariance, they're uncorrelated, which is unlikely. So what I think is happening, okay, imagine if you would, actually, yeah, I could get my whiteboard out for this. Where's my whiteboard? There it is. Okay, imagine if you would, and this is just my imagination here, okay, I'm really hoping you guys are like giving it, oh, still for my whiteboards. Is it working? It should work. Is that working? It is. Great. Control Z. Okay, so if we had a regression that looked like this, okay, because it was a simple regression before, and remember it had no constant, so we had something like essentially just, yeah, beta 1 x plus u. This is what it would look like, right? If I add in a constant, okay, like this, it has to be somewhere along here. Okay, I doubt the constant is negative, although it could be, perhaps. But yeah, okay. But okay, let's go for both, essentially. So say the constant is here, okay? And say the data is scattered along here, roughly like this, okay? If the constant is up here, I feel like the slope is going to decrease in relevance to the data, okay? Again, lots of feelings here, but I feel like this is the case, right? Because it has to actually go for the data. It's not going to go more positive because then it will move away from the data, okay? So that's the case. Even if it goes down, if it goes down, it's going to have to increase in steepness in order to match it, okay? So what I'm saying is that when beta 0 goes up, beta 1 necessarily goes down in order to adjust, and vice versa. So if it goes down, that goes up, okay? So I'm saying that these two have negative covariance, essentially, because they're inversely proportional to each other, okay? Again, grain of salt, massive grain of salt. But yeah, so then you use this. Now, because you're adding in another variable for explanation, even if it's constant, the beta 1 value, our gradient, is going to go down. So I used going down, and covariance is negative, and I think it's a positive bias. Okay? I think there's another way of doing this. If someone could find it, great. If not, this is my answer. Okay? All right. Okay, now to move on to something I'm a bit more confident in. Yeah, let's move on to question 2. So question 2, I'm a lot more confident in, so you guys are A-okay. Here's the question. Let me keep this up, and then I'll bring up Stata and move that in. Can I shift? There we go. Look at that. How fancy. Ooh. Yeah, okay. So I've done a very clear explanation here, so I was happy with this. So yeah, let me put away my pen tablet. Go for that. Let me check I'm still recording, because I would hate this long of a video to work. I'm still recording. Hooray. Right. So I've done the descriptions here. So first of all, we download the cohort data small from the Moodle page. I think I've already shown you guys what that is. It's in that little section. And then the cohort description file. We don't really need this. I can describe this to you, but I think you guys guessed what it is already, so it's all right. Estimate the sample correlation between Math 11 and years of school. Now, it's very simple how to do this in Stata. You just say correlate. Oh, I should probably bring this up. Some people would have their Stata license expire because your Stata license expires at the end of the year. This is just for security reasons, I assume, because so many criminals these days are doing advanced statistics. Yeah, the thing is, you need to go back to the student download page, and they'll have a new verification code and authentication, like all that new stuff. It'll just be on there. You don't necessarily have to re-download the entire package. You just need to enter in the new codes, and it should work fine. If not, re-download it. It'll work fine. But yeah, that's basically my deal. Also, ooh, there's my name. Good with my title. Okay, so back to that. We start by correlating Math 11 years of school. So that's Math 11 is your mathematics score when you were 11 years old. I think my one was like 6A, if anyone remembers weird like SAT grades. You press that. Oh, fuck's sake. I misspelt it. Math 11 years of school. Hooray, we have it. So we have the correlation coefficient, which is 0.4195. That's what you should roughly get. And I'm just checking what I've got before. So that's that. Yeah, so we see it's sitting around 0.4195, which is about a pretty strong relationship between the two variables. Okay, you don't have to comment on this stuff. You don't have to write as long as I did. I'm just doing it so I can explain it to you guys. Okay, then we regress log pay, the natural log of weekly pay when aged 42, on years of school and Math 11 in that order. So we're reporting on the coefficients with this standard error, and we're interpreting that as well. So you can, for a regression, you type reg or you can type regress. Literally either. I'm going to do regress just because it's easier for you guys to see what I'm doing. And then we're going to start with the dependent variable. No, we're going to start with the independent variable, which is log pay. Then we do years of school, making sure to spell it right. And then Math 11. And there we go. And now I'm just checking that that matches what I got. Oh, I did it in a different order. I was worried there. Oh, God. Okay. Well, here's what you should have. It matches here. So we can see that the coefficient of years of school is around 6%. It's 5.98% pretty much. So that implies that whenever I get an extra year of school, my wage should go up by approximately 5.98%. That's about what it means. Similarly with math, like an extra point in the math score would mean I get a 1.4% bump in my wage, roughly. And we can see the standard errors here are basically, yeah. Did I comment on the standard errors? I did not. That is something for me to do. They're small, essentially. The standard errors are quite small, so I think we don't need to worry much about them. Hold on, let me add that in. This coefficient applies. Are small. So the coefficient is likely accurate to likely an accurate estimate of the real coefficient. There we go. At least that. I do not know if standard errors are necessarily scale proportionally to the coefficient, but what it looks like is that it's small. So I think it's good. Anyways, yeah. So that's that. Now moving on to C. Estimate the following model. So a lot of people might have issues generating one of the variables for this, because I'll show you what happens if you don't do it correctly. So let's say I go about this and I'm typing in things. I don't know what voice I was going for there, but I certainly went for a voice. Years of school, Math 11. Now, if you were to usually do a variable in Stata, you would simply write 2 at the end, just like that. But as you can see, that ends up with Math 112, and as you can see, the variable wouldn't be found. So with variables ending with numbers, you have to generate a new one. So you can type gen or generate, either or. Gen is a little easier sometimes, so I just do gen. I know I said everything about being legible, but I'm throwing that out the window. So gen, you type in what you want the new variable to be called. Here I called it square, so sq math11, and you basically say that's equal to math11 squared. And I've done it. It shouldn't pop up with anything. It just says that. Now I can redo that. I'm going to copy because I'm lazy. And then I'm going to add in square math11, and you should get this. And if I did that right, it should match. Good. So it should look like this. Then we want to talk about standard errors and R squared. So the R squared here is 0.1288. That means there's a lot in this, a lot of variance that isn't actually explained by the I explained it properly here. Yeah, here we go. The regression fit is less than optimal. The standard error for years of school appears fair, but the standard error from Math 11 is quite high. So you can see the standard error from Math 11 is higher because, oh yeah, you want to talk about it as a proportion of the coefficient. So the standard error for example, our last one would not be proportional to the coefficient. As you can see, it's quite small. So there. But you can see that the standard error is quite high for Math 11 here, because it's quite close to the number. So that's sort of what I was going for. The R squared value is low because a large proportion of the variance in the sample is unexplained by the regression. So variance in the sample is what it measures. So there's a large amount of variance in the sample that is not explained by this regression. That's what I'm going for. Then we talk about the individual ones. So it's the same thing. Extra year of school, 5.99% increase in wage. Extra grade in math, 1.5% increase in wage. And because the coefficient of square math is so small, it's essentially irrelevant. Okay, so it is technically combined with Math 11 to give a cumulative thing, but because it's so low, we don't really need to consider it. So that's what I commented about. Now, basically, to consider how important it is, you can derive to get sort of the relationship. So here we say that an extra point in math would basically increase it by this function here. So increase it by this minus this small amount by Math 11. Okay, so what this essentially implies is that there's diminishing returns. So as your math score, which side am I coming in? This side. As your math score increases, it starts to sort of plateau. That's what that final term is going to be about. Basically, it's just going to plateau. The returns to extra marks basically plateaus as you go. But yeah, that's that. I have to be quick because I have to go soon. Based on the regression fit you found in C, which was what we just got, what is the marginal effect of an additional point on maths test for someone with a math score of 20 and a score of 50? Okay, so now we use our coefficients to basically calculate what's the marginal effect. So all you have to really do is just plug in numbers and then compare. So I plugged in for 20 and I plugged in for 21, which is, again, what I used here. So remember to use this. Okay, use this derivation. So you plug that in, you plug it 20 and 21, you find the two outputs, and then you basically say, okay, what was the overall effect? And here it was 0.0146545. And then for 50, I did 50 and 51, and I did the same thing, and I got 0.0139614, which proves the diminishing returns, because we have a larger effect at a smaller point score and a smaller effect at a large point score. All good? Hopefully it is. Then we do, verify that the SS column of your Stata output, you can take the ratio of model S. This is super easy. Basically, take this number, divide. Oh, it's the same as R squared. Shock. That's literally it. Now for F, estimate beta 1 in the partialing out algorithm. Now the partialing out algorithm is brought up somewhere here. One moment, Control F, partial. Oh, it's here. Yeah, I just didn't look down the page. Yeah, so these are the steps. So actually, there's a YouTube video that I used for this. I would have to go through my history though. I don't really want that getting out. Not because, oh, for fuck's sake. Hold on, let me pause. Got to make sure I'm pausing this. And this is the stop button. I pressed the stop buttons before and I don't like it, so I have to pause. Never mind, I didn't even have to look through my history. Let's, it was on my laptop, so stuff like that. Let's do, so partialing out algorithm Stata. No, that's Stata. I think it was this one.
Hello, everybody.
No free cred. Yeah, this video here also helped out a lot, but I'm gonna go through what I basically did just because it's a little easier to see it a bit more tangibly. Okay, so back to it. So what we do essentially in the partially out algorithm, what is this said? Actually, the question tells you quite easily. First, regress years school onto math 11 and math square. So what we do then, okay, is we're going to do regress years of school, math 11 and square math 11. We get that. Let me check it matches. It does match. Hooray. Then what we have to do is the command to save the residuals. Now, they don't tell you this, so I'm going to tell you it's predict. So you say predict, and you essentially predict for the variable. So you do r/the variable you want to predict. Here it's math 11, then comma r, and it will do it. And let me do that for square math 11. That's the command. Then what we do is we do a regression with linpay with the residuals. So regress, I'm just going to do reg now, linpay r math 11 and r square math 11. There we go. So that's what you should get. And you can see here that r square math 11 was omitted because of collinearity. Okay, and I haven't filled this in. Fuck. Okay, so essentially r square math was omitted because it is directly a function of square of math 11, which is fair, right? Because it's literally just the square value of that. So that kind of stuff gets omitted automatically in Stata, so you could comment on that. So commenting on your findings. Oh, God. Live, you're seeing how I'm fucking up. Fuck. Yeah, so essentially, we can see here, this is basically the same as our previous coefficient. So if you look here, we have 0.599, and then if you look at this one, 0.599. So it's the same. Wait a second. Hold on. I think something's gone wrong here. My brain's exploded. It's 338. 338. Yeah. Oh, right. Of course. Sorry. That's the, Fuck. Yeah, essentially the thing you set as the independent variable for the start is the thing you're retrieving the coefficient for. Just don't worry about what the residuals are called. Just remember that years of school is the coefficient that's being partialed out in this algorithm, not math 11. And then you won't look stupid like I am. But yeah, that's basically it. So residual of square math 11 gets cancelled out because it's product of R, it's product of math 11 residuals already. And we basically now said that, the coefficient is the same. Of course, these slides, it looks like, it's OLS and multiple linear regression. That gives you more detail, so look at that. But yeah, that's essentially, just look here, and I don't know if this one has a partially, there's the thing. I don't know if this one has partialing out algorithm. Well, yeah, it has it there, but it doesn't have as much detail. So look at that. And then our final question, which I shall bring up now, constructing the PEXP variable, which is age, years of school, minus 5, which is potential work experience. We then estimate the following regression, and we do get, actually, let me show you how to do this as well. I will really have to be quick because I have to leave soon. PEPX, actually, one moment, I need to check my phone. Just over here, doing nothing in particular. Don't, what the, okay. All good, nothing so far. But yeah, So PEPX, we need to generate this. So gen PEXP, which is equal to, and it says age minus years of school. Let me just sit up straight. Minus 5. I think that's correct. Yep. And we generate it. Looks fine. Now let's regress LearnPay on years of school, math 11, and PEXP. And as you can see, PEXP was omitted. Why? Because of perfect collinearity, okay? And it tells you that there, doesn't it? So pretty easy to see. Basically, the idea is because PEXP is a combination of other variables, it's perfectly collinear to years of school of math 11 because it is made of years of school, essentially. So because it's made of years of school, it doesn't work, essentially. So it gets omitted automatically from Stata. And yeah, I think that is pretty much it. Okay, thank you for watching a bit of a freak out, but that's that. Sorry I couldn't get more on 1E or 1F. The problem is normally when I make videos, I have to know the answers before I go into it, but I thought it was useful for me to at least put something out instead of just giving nothing, because the Stata stuff might be useful to someone and I didn't want to handicap myself, basically. But hopefully that was useful. Yeah, hopefully everything went well there. Remember to look at the lecture notes and the slides. They're really important. And yeah, good luck, I suppose. Yeah, all right, I better end it then. All right, see you guys. Bye.